Okay, Lama, let's start the second session for today. Right, this is about the electronegativity. Right, now we are going to discuss about the concept of electronegativity. The last period trend we are going to study right under this lesson. Right, electronegativity. What it means? What it means? The electronegativity. Right. The definition is the ability to attract the electron pair in a covalent bond towards the constituting atom is referred to as that atom's electronegativity. Right? Let's have a quick idea about that thing. So it says the definition is ability to attract, right? Sorry, writing in different color. Definition is ability to attract right the electron pair in a covalent bond towards the considering atom. Right? This is the definition. Right? This is the definition of electronegativity. Ability to attract the electron pair in a covalent bond towards the considering atom. Right? So one can say it's a measure of electron deficiency. One can say it's a measure of electron deficiency. Right? That is another way of looking at the electronegativity. Right? It's a measure of electron deficiency. Right? The idea is clear now. If you are more electron deficient, so if electron deficiency is high, then you tend to attract the electron pair in a covalent bond more towards yourself. Attracting the electrons becomes greater. When you are more electron deficient, you try to attract electrons greatly. That will ultimately lead to greater electronegativity. It is high, right? So it's a measure of electron deficiency, one can say. Right? So this is the concept of electronegativity. Greater the ability to attract the electron pair in a covalent bond towards yourself, your electronegativity is high. Right? See the idea. So when you examine these values in your periodic table that is given in the note, you clearly see two trends. What are the major two trends here? The first trend we see is going towards right, going towards right, going towards right, going towards right of a period. Right? Going towards right of a period. The electronegativity increases. It really increases. See, 0.1, 1.0, 1.5, 2, like that, it really increases. That is one trend. That is a period trend. Going towards right of a period, the electronegativity increases. What happens with this? When going down a group, electronegativity decreases. Electronegativity decreases. That is the major two trends you should absorb from these numbers. Let's discuss the reasonings behind those two trends. The thing is Islam. Let's think of two atoms. One is larger and one is smaller, forming a covalent bond. Forming a covalent bond. Let's say this is X, this is Y, forming a covalent bond. Right? This is the sharing pair of electrons. These are the two nuclei. These are two nuclei, right? So small atom and large atom. I'll take this one like this. Small atom and large atom. Right? So you clearly see ability to attract this electron pair, this shared electron pair. Right? The ability to attract this shared electron pair is greater as the nucleus of the small atom is more closer to that. The ability to attract the electron pair towards it is greater with the small atom compared to the large atom. Compared to large atom, because the large atom's nucleus is bit away from the shared pair of electrons, but when it comes to small atom, it is more closer to the nucleus is more closer to the shared pair of electrons. So ability to attract the electron pair by the small atom is greater than the large atom. So one can say electronegativity, which is denoted with this, is high here. Electronegativity is of this is, let's take it as AB, then you mix up, no? If not, electronegativity of B is greater here, electronegativity of A is smaller there. So with this, it is very clear, right? When the atom becomes smaller gradually, normally, right? If you are thinking of same period or same row, right? When the atom becomes smaller, the electronegativity increases. So that is what happens with these rows, with these periods. Going to the right, the atomic size decreases. So ability to attract the electron pair towards the atom increases. Right? When going down, what happens? When going down, atomic size increases. Atomic size increases, so that ability to attract the electron pair decreases, right? As the electron pair is bit away from the nucleus, right? So that is the idea. So this is valid when, right, considering periods as well as groups, right? So you have a node there in that space, you can write this, right? So just write this one. This is written there, so it's a measure of electron deficiency. You can write this one. It's a measure of electron deficiency. So you can start with this point. Electron is a measure of deficiency, electron deficiency. But the electron deficiency is high, the electron is high. This is about the size. This is about the size. The second point, right? You can say, right, going towards right a period is valid for basically S and P block, right? Right? Electronegativity increases as atomic size decreases, right? So other thing is, when going down a group of elements gradually it decreases. Decreases as atomic size increases. Right now, those are the major things you should know. Right? The common trends. Going down as atomic size increases, it will decreases. Going to the right as atomic size decreases, electricity increases. Right? Okay. Next point. With each and every period trend, normally we have discussed about the maximums and minimums. Here also we'll discuss about the maximum values. The maximum values. Right? Maximum values. Maxims. Right. Okay. So maximum values. The maximum values. Maximum values. Right? Okay. When it comes to maximum values, right? You see, the point is this. As we have said, that going towards right, as the value should increase, and coming up also should increase the value. So the maximum value should appear at the upper right corner. Going towards right, the value increases. Coming up, value increases. So the greatest value should be at the upper right corner of your period table. So fluorine means fluorine is the one with the greatest certainty value, greatest certainty value. So basically, certainties are not assigned for noble gases. Certainty values are not assigned for noble gases normally. Why is that? Because with the definition, it says certainty is all about ability to attract the electrons in a covalent bond. Ability to attract an electron pair in a covalent bond. So, in a covalent bond, right, the ability to attract the electron pair. That is the electronegativity, right? But you know, when it comes to noble gases, right, those are not that much keen of making bonds. When it comes to the smallest noble gases, right, smaller ones, helium, neon, argon stuff, those are not keen to form bonds. So electronegativities are not defined then, because not forming covalent bonds. So no ability to attract the electrons pair in a covalent bond as you are not forming covalent bonds, right? So but xenon and radon, slight bonds are formed basically with xenon. You will see the xenon oxides, XeO2, XeF4, XeF6, XeF2. Xenon tends to form some bonds with the fluorine and the oxygen. That is why some value is assigned for xenon and radon then. So, but not with the small noble gases, right? We'll discuss how they are able to do so, to form bonds with the last section of the of this lesson. The second interactions, the London forces, right? Okay. So anyway, so the greatest value should appear with the element appearing at the upper right corner, right? Except the noble gases, right? That is fluorine. So greatest value, the maximum value, is with fluorine. Fluorine is coming up with the maximum value. Then next highest, the race for the next highest, or the race for the second place, is actually by the oxygen and chlorine. Oxygen and chlorine. So this is the highest. Then going towards the year, the decreases, the value decreases going down as well. So next highest should be from one out of oxygen and chlorine. The oxygen wins. As it is second row, it is smaller, the oxygen wins. The next place comes with chlorine. The race for the second place was with the oxygen and chlorine. So oxygen wins. then third place is gained by chlorine. The fourth place is 1, 2, 3. The fourth here, fifth here. 1, 2, 3, third place, fourth place, fifth place. So then you have the night here, then you have the bromine. Right? Okay. Then next stuff. 1, 2, 3, 4, 5. Sixth place. So we forgot the sulfur, right? Sulfur is also there. It's also related to this stuff, right? The sixth place actually belongs to sulfur. And the iodine and carbon, the stuff are there. So we can write it as BrISC. Right? So even though the values appearing at the first resource book is 2.5 for both the sulfur and iodine, at the unit 6, those values are given as 2.6. So prefer both the values, right? At the unit 6 resource book, the sulfur and iodine neutrality values are given as 2.6. Or prefer those as well, while the carbon's value is still stand at 2.5. So that is why the carbon is a smaller value than this. So bricks, just exchange these two. Brisk, F4ClN, brisk, right? So those are the first 8 elements with the greatest utilities. All others are less than that. Better to know these values as well. This comes with 4.0, 3.0, 3.1 and 3.0 again, and this is 2.8, sorry, this is 3.5, sorry for that. 4.0, 3.5, 3.1, 3.0, 2.8. These two carry some 2.6 value, while this comes with 2.8. For a better result, you should know these values as well, right? Should know these values as well. 4.0, 3.5, 3.1, 3.0, 2.8, 2.6 and 2.8, right? Okay. So those values should be known. Other than that, some special things also should be known. What are those? The value of phosphorus. The value of phosphorus is same as the value of hydrogen. This is also asked in question papers. Value of phosphorus is same as the hydrogens. So know that as well. Right? Know that as well. Right? It is not a maximum value, but just know that the hydrogen and phosphorus are with same values. They will ask a question. Which element is with the same neutrality value as hydrogens? It is the phosphorus, right? Should know that thing. Right. What else we should know about these trends? About this trend? Right. Another thing should be known. These are the major stuff everyone should know. These are the major stuff everyone should know. Right? Then we should know these few points as well to come up with a better mark to exceed 85 marks, 90 marks. Better to know these things as well. Right? This trend, see? What to see with these numbers? You clearly see. So if you know the fluorine's number and the oxygen's number, that is enough to come up with all the numbers appearing at the second row. Just decrease him by 0.5 unit. Just decrease him by 0.5 units. 4.0, 3.5, 3.0, 2.5, no? Just decrease him by 0.5 units. Just know that as well. Then it comes to third period, the third row. Again a pattern appears. You should know these three numbers. These two will be covered by the maximum values. 3.1 and 2.5 will be covered by the maximum values. And the phosphorus value will be covered by, as it is equal to the hydrogen's value 2.1. After this 2.1, you should know that the values will decrease by 0.3 units. 2.1, 1.8, 1.5, 1.2 and 0.9. Values will decrease by just 0.3 units. Right? Actually, this is referred to as the Pauling scale of electronegativity values, Pauling scale of electronegativity values, right? Okay, you may have learned this thing in your O levels as well, right? That is how the values are assigned, the reasons behind these values, right? Okay, greater the electronegativity, that means greater your ability to attract the electron pair towards yourself. That is the idea, right? So these are the stuff appearing with your resource book, the first lesson. In your resource book, at the first lesson, these things are discussed. You should know these ones, right? With the first lesson, right? Okay, right. So you can go through the note, right? The table is given, and you can clearly, right, write these things at the special note there. So at the bottom of that page, there's a space given as per some special note. So write this thing, right? Okay, this is all about the things discussed at the first resource book. This is book of the unit 1, right? But when it comes to the A-level paper, when it comes to MCQs in your paper, A-level paper, right? Not only the stuff at the first resource book will be asked, right? The MCQ paper is designed from all the syllabus. So you should know much more about the unity concepts, much more concepts about the unity, which are actually appearing at the unit 2 as well. So few more concepts are there with the unit 2 as well, right? We'll discuss about those things also at this point. Then we are with a clear, complete note about the unity, right? Okay, let's discuss about the things appearing in the second unit resource book, right? That is also needed to answer the papers, right? Questions in your papers, right? Okay, let's go to there, right? Right. So we'll discuss the major concepts we should know about the electronegativity, that which are appearing actually at the unit 2 lesson. Right. First we'll start with the usages of electronegativity, the applications of electronegativity, right? Applications. Right? So the concept of electronegativity can be used to determine the polarity of an covalent bond. To determine the polarity of an covalent bond. Right? Determine the polarity of an covalent bond. Of a covalent bond. Let's discuss what is this, the polarity of a covalent bond. So let's think of a situation like this. So if you are to think of the Cl2, even the H2, right? We know the chlorine guys are with 3.1 electronegativities. So the shared pair is actually at the center. Both atoms are with equal strengths of attracting these pair of electrons in the covalent bond. So the pair of electrons occupy the center of the covalent bond. Even with this, at the center. But But when you are to form the HCl, when you form the HCl, as you are dealing with two atoms with two different electricities, then what will happen? The shared pair will be greatly attracted by the higher electricity atom. The shared pair will be greatly attracted by the higher electricity atom. That means the shared pair will appear here like this, more towards the higher electricity atom. The shared pair will appear right more towards the higher electricity atom. So the electron density is not symmetric like this. Electron density is not symmetric like this. These are symmetric electron densities. But here the electron density is more towards the chlorine. More negative nature is there with the chlorine. Less electron density there with the hydrogen. So these bonds are referred to as polar bonds. These kind of bonds are referred to as polar bonds. Why is that? Because you have two poles there. You have a greater electron density at the chlorine side. So we'll mark that as a negative delta. And you have a less electron density at the hydrogen side, positive delta. Negative delta means bit of a more negative charge is there. Bit of a more negative charge is there. Delta means a very small value. A small negative charge is created here. So more positive charge should create here because the electrons are now gone towards the chlorine. So this kind of a bond is referred to as a polar bond. Polar covalent bond. Right? While these kinds are referred to as non-polar covalent bonds. Right? So to decide the polarity of your covalent bond, the electronic concept is much needed. If the bond is created between two same electronegative atoms, the electron pair resides at the center, so no polarity will appear. If the covalent bond is formed between two atoms with two different electronities, the electron pair will attract greatly towards the more electronegative atom, creating a negative pole there. And the other side you create a positive pole. So some poles are there with this covalent bond. So polar covalent bond, right? That appears when you are dealing with two atoms with two different electronities. So determine the polarity of the covalent bond. The electronic concept is important, right? Then at the latter section of this sections of the second lesson, they will discuss about the magnitude of the polarity. About magnitude of the polarity. So it is also like that in Laman. So if you are thinking of the polarity of the HCl, that will differ compared to the polarity of HF. So HF is with fluorine, which is more electronegative than the chlorine. So that bonded pair is more towards the fluorine, like this. No? More towards the fluorine. So creating a greater negative delta there compared to the situation here. No? Greater negative delta. So polarity is high here. See? Polarity is high here. Right? So the idea, no? Okay. So the magnitude will also discussed with the equation. The magnitude is also discussed with the equation, right? And a parameter called dipole moment. Dipole moment. Magnitude will be discussed with the equation and a parameter called dipole moment. The dipole moment. This will be further discussed. That will be given by delta R, right? That will be further discussed with the intersection of the unit 2. There I will discuss more about that thing. Dipole moment is a parameter used to get the magnitude of the polarity of a polar covalent bonds, right? So that can be taken with multiplying the delta, the partial charge, by the bond length, the distance between two nuclei of the atoms. That is how the dipole moment is measured, which is a measure of polarity of your bond, right now. So that is the idea. So to determine the polarity of the covalent bond, you need the data about the unity. The second thing, second application, these are there in your note, right? The second application, second application, second application. The second application is actually, so you can predict whether a bond is covalent or ionic with the use of unity values, right? To decide whether a bond is covalent or ionic, we use the unity data. See what we can use there. It is like this. When the unity difference between two atoms, let's say X and Y, so A and B, let's say take it as A and B. The unity difference, unity of this thing, let's take it as XA, that XB. The delta value means the difference between those two, right? Delta value means, delta X means difference between those two. By considering that delta X, you can predict the bond, whether the bond is ionic or covalent. If the delta X is exceeding 2 units, then we prefer such a bond as ionic bond. If the difference is less than 1.7 units, normally we prefer such a bond as covalent bond. With the use of this theory, we can determine, right, whether the bond is covalent or ionic. Let's apply this one to few molecules, then you will see, right? Okay, let's come up with some molecules. NaCl. NaCl. This guy is with 0.9, Cl is with 3.1. The difference is 2.2. It is exceeding 2 units. That means the bond is ionic. The bond is ionic. Right? Let's think of another one. Right? Think of another one. So another thing. Potassium fluoride. Potassium, right, comes up with 0.9 kind of number. Fluorine comes up 0.0. The difference is what? 3.1. Definitely it is exceeding 2 units. It is ionic. Some more. Let's think of H2O. Hydrogen is actually coming up with 2.1. Oxygen 3.5. Difference is 1.4 units. It is less than 1.7. So that the bond is covalent. See, you can print. The NaCl appears like this. KF appears like this. H2O, it appears like this with covalent bonds. Another thing, HCl. See, 2.1, 3.1. The difference is just 1 unit. So it is covalent. So you are supposed to write a dash between the H and Ca. Dash covalent bond. These are just ionic bonds. Ionic attractions. Ionic attractions will connect the particles. So you can apply this theory to predict whether the bond is ionic or covalent. For most of the compounds, this is valid. With very few occasions, this will be violated. But as a rule, you can take this one, right? Okay. So that is about the predicting the covalent ionic nature of a bond. So that is another very important application regarding the electronegativity values. Right now. Okay. After this, we'll discuss about few more stuff we should know about electronegativity. Right? Few more things about electronegativity. Right. Next one. Let's come to the next one. Right? So these things are in your note. Just go to the note. You will see those, right? Okay. Right now. Then few things should be known. Few more stuff, right? Let's discuss the next things you should know about electronegativity. The next point. It is said that electronegativity is right not a characteristic no a constant value for a considering atom. This is very important note. It is not a characteristic nor a constant value. Not a characteristic nor a constant value for a considering atom. What it says? It says, let's come up with the characteristics form. So you know the 2.1 value is not a characteristic for hydrogen. 2.1 value is not a characteristic for hydrogen. So even the phosphorus is with the same 2.1 value. So 2.1 value can have by both the phosphorus and hydrogen. So it is not a characteristic value for one given element. Even 2.6 with the sulfur and iodine. See, those are not characteristic values for a given element. This first thing. The second thing, that is the most important stuff here. Not a constant value for not a constant value for a given element. That is also important. Not a constant value, right? That means it's not a constant value, right? I'll write like this. It's not a constant value. So it will vary. It will vary with the chemical environment. So you can say the electronegativity, right? Electronegativity will vary with the chemical environment of the atom. Vary with the chemical environment of the atom. Let's discuss what it says. Let's discuss what it says. So the idea is this, right? The 3.1, the 3.0 value for the nitrogen. Normally the Pauling scale says that the nitrogen value is 3.0. No, this point says nitrons, always the nitrons are not going to carry that 3.0. The 3.0 value may vary with the nitrogen, with the chemical environment of that nitrogen. This is what it says. So it should be noted null amine. The idea is this, no? See, if a nitrogen is if a normal nitrogen connected to hydrogen, and if a positively charged nitrogen connected to hydrogen, if you are referring to these two guys, right? This guy's electron deficiency is less than this one. No? This one's electron deficiency is high compared to this one. Is low. So that this guy tends to attract the electron cloud more towards that atom compared to less strength here. Because this guy is greater electron deficiency means this guy tends to attract the electron density of this NH bond greatly compared to this one. That means the electronity here is high than the electronity here. See? So both can't carry the 3.0 now, no? So if this value is 3.0, this value could be 3.1, like that. Right? So the value of electricity will vary with the chemical environment of the element, of the considering element. Right? So such 4 chemical environments have to be studied. Such 4 chemical environments have to be studied under this section. Let's study one by one. Right? Let's start studying one by one. Okay. Right? Number one. Quickly, we'll go through those things. Number one is the hybridization of your atom. Hybridization of the atom. The point is this, the hybridization, right? It's like this, no? So I'll write the hybridization. Right, the shape, so hybridization, there is character and the shape. So we have few hybrid orbitals. It could be sp, sp2, sp3, the hybrid orbitals. This character, out of 2 orbitals, you have 1 s orbital. Out of 2 orbitals, you have 1 s orbital. So s character is 50%. Here, out of 3 orbitals, you have with only 1 s orbital. Right? The s character is 33%. Out of 4 orbitals, 1 s orbital and 3 p orbitals, 1 is s character is 25%. Right? The shape, the sp orbital is more spherical, having more properties of s, as s character is high. When it comes to sp, that carries bit more p properties, lengthier situation than the sp. sp3 is with more p character, so more lengthier than the above 2. These are the shapes of 3 hybrid orbitals. So when it comes to sharing pair of electrons, let's say here the sharing pair appears. When it comes to sharing pair of electrons, you clearly see the sharing pair of electrons are more closer to the nucleus of sp orbital than in sp3 orbital. So here the sharing pair will be greatly attracted. That means electronegativity is high. For here, much less, and here very less. So going up, we can say as its character increases, the utility increases. As its character increases, the utility increases. That is the first point. One can say its character of hybridization increases, the IO electronegativity increases. So just highlight that stuff, box that stuff, right? Let's come up with the example. Let's come up with the example for that, right? Okay, let's come up with the example for this situation. If you need an example, right, I'll write it here. For example, right, for the hybridization of data. So let's discuss about these two guys, the NH3. Sorry, let's discuss about another two, the NO3 minus and NO2 plus. With the NO3 minus, the structure is this. The structure is this. With the NO2, the structure is this. Structure is this. Right. Let's discuss the utility of nitrogen, which is the greater value and which is the smaller value. Right. So here, the hybridization is sp2. Why is that? Actually, by counting the sigma bonds and lone pairs, you can come up with the hybridization. Here, the summation of sigma bonds and lone pairs, 1, 2, 3, 3 sigma bonds and no lone pair. 3 units, that means S and 2 P's, sp2. Here, the summation of sigma bonds and lone pairs, only 2 sigma bonds, no lone pairs around the nitrogen. So, just 2 units, that is sp. Right? Always between two atoms, the first bond is sigma, the others are phi. The first bond is sigma, the others are phi. Right? So only 2 sigma bonds are appearing. Here, 3 sigma bonds are appearing. This other thing is phi. So count the sigma bonds and lone pairs on the considering atom. If that is 2, the hybridization is sp. If that is 3, the hybridization is sp2. If that is 4, the 1 is and 3 p is sp3. That is how you come up with the hybridization by just looking at the sigma bonds and lone pairs. Right? So we can say this character is character of, right, sp2 is lesser than sp, right? We can say the electronegativity of nitrogen, it comes that for NO3 minus is smaller than NO2 plus, right? The one with the greatest character is with greater utility, right? No? Okay, so that is the example. So you can put this example as well with that note, right? No, that is the first thing. That is the first example, the first chemical environment we need to discuss when it comes to utility. So utility of nitrogen is in this case is larger than the utility of nitrogen in this case. That is what your S character does, right? No, okay. let's discuss about the second chemical environment, right? Second one. Right. Number 2. Right. Right. Number 2. Sometimes we'll come across situations where the hybridization is same. Let's consider these: the OH minus, H2O, and H3O plus. If they have asked you to come up with the affinity of these oxygens, the variation, right? You will come up with the correct question. Why is that? Because the hybridization is same. Counting the sigma bonds and lone pairs will give you 1, 2, 3, 4. 4 it means sp3. With this one, counting sigma bonds and lone pairs, 1, 2, 3, 4. 2 sigma bonds are there. So that is sp3 again. Counting sigma bonds and lone pairs for this one, again 3 sigma bonds, 1 lone pair, 4 units, that means 1 s and 3 p's. The hybridization is same. Hybridization is same. This character is same. So we can't use the earlier technique to come up with the affinity of this one. So that we go for the second consideration. That is the charge on the atom. Charge on the atom. Charge on the atom. What it says? It says when the positive charge on atom, the positive charge on atom is high, your electronegativity is high. That is what it says. Right? When the positive charge on your atom is high, the affinity is high. It is very clear, right? When the positive charge on your atom is high, that means your electron deficiency is high. Your electron deficiency is high. So that electron deficiency is high. That means the electron deficiency should be high. Right? So we can say that the charge on atom, charge on oxygen atom, when it comes to the charge with OH minus, you have just -1 charge. With H2O, you have 0 charge. With H3O plus, you have +1 charge, which is greater. So the affinity of oxygen is least with the OH minus, then with the H2O, and greatest with the H3O plus. The charge on atom, here the -1, here 0, and here the +1. The charge on the considering atom, the oxygen here, right? That also decides your affinity. So affinity of oxygen here is greater than the affinity of here. That is the second consideration. Let's quickly come up with the third one. Right? The third consideration. The third one. Some situations are there where the charge is also the same. See this one. NH3 and hydrazine, N2H4. The NH3 molecule is this. N2H4 is this. if you have to consider the charge, that is also same as well as the hybridization. The hybridization of this nitrogen is actually you have 1, 2, 3 sigma bonds and only one lone pair, that is 4 units. That means SNP3, sp3, 1 SN 3 Ps, the 4 units. When it comes to these nitrogens, they are also coming up with 3 sigma bonds and a lone pair, 4 units, sp3. Even this one is sp3, right? Hybrid is same. Then charge is also same. Charge is 0 on both of nitrogens. So then what we can use to come up with the electronegativity variation of these two nitrogens? That is referred to as the oxidation state. Oxidation state. So it says when positive nature of oxidation state is high, or the oxidation number one can see, when that is high, we can say the electronegativity is high. Right? That is the idea. So again the electron deficiency comes to play. Right? What this means, the oxidation state. And the oxidation state means that as a definition, it says the charge on the atom if all the bonds are referred to as ionic. The charge on your atom if all the bonds are referred to as ionic. Let's see. If this bond is ionic, the more towards the more electronegative atom, the electrons are attracted. That means this forms a negative charge and this comes with a positive charge. If both the electrons are going to come towards nitrogen, this gets a negative charge and this gets a positive charge. Charge on atom if the bond is considered to be ionic. For this one, it is again minus and plus. It's again minus and plus. The more electronegative atom gets a minus, the other atom gets a plus of a covalent bond. For these, this is minus, this is plus. This is minus, this is plus. For this bond, no charge variation because the electrons are at the center because those atoms are with same electronegativity values. So the charge of this thing, if all the bonds are referred to as ionic, is minus 2. That is your oxidation state. Oxidation state. For here, the charge is minus 3, 1, 2, 3, minus 3. The oxidation state is minus 3. So that is the third point. So charge on atom. We can say, right, we can say the hybridization is same. This P3. Then your charge on atom, charge on nitrogen is same, 0. Then comes the oxidation state. Oxidation state of nitrogen. It is greater, the positive nature is greater in N2H4. Right? For NH3 is minus 3, but N2H4 is minus 2. So that you can say, so that electronegativity of nitrogen is greater with N2H4. See, that is the point of charge oxidation state. Right? Greater the electron deficient you are, more your electronegativity is. That is the same idea, right? Greater the positive nature, greater electronegativity is. So here, less negative nature means greater positive nature. There you have the greater electronegativity. Right? Okay. Let's come up with the final one. The fourth one. Quickly. Right? The fourth case. The last one is actually referred to as the connected atoms. Connected atoms and they are electronegativities. According to this theory, it says when the connected atoms are with greater utilities, utility of connected atoms are high, then your considering atoms electronegativity is also high. Utility of considering atom is also high. That is what it says. Quickly discuss about that idea as well to wind up quickly, right? So let's consider the CHCl3 and CHF3. So you have some chlorines here and the hydrogen here. So CHF3, some fluorines here, some hydrogen here. So as chlorines are with 3.0 as well as fluorines are 4.0, this 3.1, sorry. So electrons will be greatly attracted towards the fluorines when considering chlorines, so that this guy's electron deficiency will be low, while this guy's electron deficiency is high. So greater electron deficiency, right, your utility is high, your utility is high, right? That is the ultimate idea. So you can say, right, in these cases as charge, oxygen state and the hybridization all are same. Hybridization, charge on carbon and oxidation state of carbon all are same. Then what matters is the utility of connected atoms. Connected atoms that differs, like chlorine is the lower utility than the fluorine, so that electronegativity of carbon varies, like CHCl3 is having a lower utility than CHF3, right? No? That is the whole idea, right? Okay, right. So you can complete the note, just take a screen capture and complete the stuff, right? So it is clear, no? Right? That is the fourth fact which affects the utility, right? No? So with this we'll wind up for today's lesson, right? Then we'll come up with the unit 2 next day, right? So thank you for listening. Goodbye then. See you next week.